Welcome to this primer on the well-ordering principle. In this lecture, we'll look at an application of the well-ordering principle to a very interesting problem about balls and bins. So let us recall what is the principle. So the well-ordering principle says that every non-empty subset of the natural numbers has a smallest element. That's it. And last time we discussed this principle and saw an application which was on the following template. So you want to prove a statement for each natural number n. What you do is you collect all those natural numbers for which this statement is false. If this were an empty set, then we were done. If this were a non-empty set, then it would have a smallest element in it. And then somehow you use your given situation to get to a contradiction. And we will use the same template in this problem. So let's see what the problem is. Fix a positive integer n, and we have been given n plus 1 bins. So n plus 1 bins have been drawn, and all of them have some number of balls in them. And we know how many balls are there in each bin. The first bin may have b1 balls, then b2 balls, up to bn plus 1 balls. So this initial configuration has been given to us. We are allowed a certain kind of move. So at any step, one is allowed to choose n bins. So out of these n plus 1 bins, we may choose n bins of our choice and add one ball to each of them. So we are given an infinite supply of balls, and each bin can hold as many balls as you want. So all those things, real world constraints do not hold. Okay, so at any step, one is allowed to choose any n bins of one's choice and add one ball to each of them. One wants to show that it is possible to have the same number of balls in each bin by a finite sequence of such steps. I haven't written the word finite here because that is already implied. Okay. So no matter what is the initial configuration, you can always equalize the number of balls in each bins after some sequence of such moves, intelligently chosen, of course. If you're just doing it willy-nilly, then it's not going to happen. So that's the problem. I hope it's clear, but let us see an example. So suppose I have these 3 bins, n equals 2. So let me draw them. And maybe the initial configuration is 2, 3, maybe 1 here. So we want to equalize the total number of balls. So how do we do it? Okay, so first I will choose these 2 bins. So since n equals 2, and therefore we have n plus 1 equals 3 bins. So we may choose any 2 bins at a time. So first I choose these 2 bins and add one ball to each of them. So here I get a 4, and there I get a 2. And now for the remaining steps, I will choose these 2 bins both the time. I will choose these 2 bins, add one ball, so I get a 3 and a 3. Oops. And then again, I'll choose the same 2 bins. Again, I will choose these 2 bins and I will get a 4 and a 4. Unfortunately. So that's basically what we want to do for a general n. Okay, so let's see. So first of all, note that for n equals 1, the problem does indeed hold. So if you have n equals 1, sorry about this. If you have n equals 1, then there are only 2 bins. And whichever bin has smaller number of balls in it, if they have already equal number of balls, then we are done. Otherwise, if they do not have equal number of balls, then there is one bin with smaller number of balls. You just keep choosing that bin and add one ball to it until you arrive at the configuration where you have the same number of balls. So n equals 1, clearly this is true. And now we will collect all the bad natural numbers. So we define a set B, which is the set of all these natural numbers for which the problem does not hold, meaning that there exists a configuration of n plus 1 bins with some initial number of balls in them, such that no matter how you choose n bins at each step, you will never be able to equalize the total number of balls in each bin. So all this longish statement I will be a little bit succinct about. So this is all those natural numbers such that, so all those natural numbers for which you cannot show what the problem asks you to show. And so if this were the empty set, then we are done. So we may assume that this is non-empty. And now our goal is to produce a contradiction. Okay, so now by the well-ordering principle, there is the smallest element in the set B. And we have called that smallest element M. This MIN stands for minimum, meaning smallest. So let M be the smallest element in this set B. B stands for bad. Okay. So now, since M is bad, we have a configuration of M plus 1 bins. Okay, so M plus 1 bins have been drawn. The first bin has B1 balls, B2 balls, then B3. Okay, so some initial configuration has been given such that no matter how you pick M bins at a time and add one ball to each of them, you will never be able to equalize. So since M is bad, so this just means that this is a bad configuration of balls. You cannot possibly equalize. Okay, so here is the point. Note that, or maybe I'll write it here. So note that M minus 1, first of all, is a natural number. Why? Because n equals 1, or maybe I should just say that 1 is a good natural number. So 1 is not here. 1 does not lie in the bad natural numbers. Hence, this is at least 2. Since this is at least 2, this is at least 1. That's all. So this is a natural number, and since this is smaller than m, this is not bad. This is good. We have m minus 1 is good. Okay. Okay, all right. M minus 1 is good. What that means is, whenever we are given m bins with some initial configuration of balls in them, you can always keep choosing m minus 1 bins at a time and add one ball to each of those bins to ultimately get a equitable configuration. Fine, so now just focus on these m bins. M is equal to m minus 1 plus 1. So many bins. We have some given initial configuration of balls in them, so we know that if we intelligently choose m minus 1 bins at every step, we will get to an equitable configuration. All right, so therefore there exists such a choice of m minus 1 bins at a time. To that choice, we just append this last bin, so that every time we will be choosing m bins from this total initial bad configuration. So this will be chosen every time, and here the choices will be made so that after some finite number of steps, we will get an equitable configuration. Okay? So after those sequence of moves, what we will get is the picture will be like this. Here we'll have same number of balls, the first m part. And here we will get some b prime balls, different possibly. So once again, what happened? This is the key step. M minus 1 was a good natural number. So here we always, since these are m bins, meaning m minus 1 plus 1 bins, we can choose m minus 1 bins at a time, increment, keep doing it so that we would get to a configuration like this, right? But we had to work with this configuration, so we had to choose m bins. We cannot just choose m minus 1 bins and leave it at that. We have to choose m bins. And hence every time we just keep choosing this also. Along with the m minus 1 that we choose, we append this one to that also, so that we are choosing m bins. And in this process, since by what we said, here we can get an equitable distribution, equitable, configuration. But this we do not have any control as of now. This was getting incremented by one ball every time, and so that's the kind of thing that we will get. So now here is the thing. So there are some cases, 3 cases. Case 1, b is strictly less than b prime. So this is a simple case. If this were the case, then what you can do is just keep choosing these m bins every time, keep incrementing up until the point where you get b prime balls in each of them. So this is a favorable case, clearly. So this is dealt with. The even more favorable case is b is equal to b prime. We just stop and report that m is actually not bad because we are able to get an equitable configuration, and so we stop immediately here and get a contradiction because m was supposed to be bad. and this was a bad configuration. And case 3 is when b is strictly greater than b prime. So case 3 I will explain by means of an example. So suppose we had this kind of a situation. So here maybe we had 5 balls, this was 5 balls, and this was 3 balls, let's say. And m is equal to 2. Okay, and we want to say that, we can actually equalize in this situation. So we are allowed to choose 2 bins at a time in this particular example. So first choose these 2 bins, then choose these 2 bins. Okay. In the process, each of these will increment only by 1, but this will increment by 2. Right? So once you choose these 2 bins, this becomes a 6. That becomes a 4. Then you choose these 2 bins, this becomes a 6. And that becomes a 5. And then you again do the same thing. Choose these 2 and then choose those 2. You will see that you will get 7, 7, 7. So you just do the same thing for the general thing. First you drop this guy and select all the rest, increment. Then you drop the adjacent guy, select everything, increment. Then you drop the next adjacent, so on, so on. So in that whole compound m step process, each of these will get incremented by m minus 1, while this will get incremented by m. And hence you will see that, these numbers are becoming closer and closer. And if you just keep doing this compound step multiple times, you will arrive at a configuration which is equitable. And that brings us to a contradiction, because in either case 1, case 2, or case 3, we are able to produce an equitable configuration, contradicting the fact that this was a bad configuration. And that finishes the proof. So this was a very nice problem. And we saw the power of the well-ordering principle. The well-ordering principle came into play in this step where we just said that since m is the smallest bad natural number, m minus 1 is not bad. And here we have a magical, mysterious way to, find a sequence of m minus 1 choices every time to get to a configuration like this. So if you're into programming, then you see that this is like recursion. And yes, indeed, this is like recursion. And in the next lecture, we'll look at the principle of mathematical induction, which looks, on the face of it, it looks much more like recursion. Anyway, so with that, I want to end this. As usual, like, comment, share, subscribe, and I'll see you next time.